Okay, we're going to get started with today's class. Before I start the chemistry portion, I do want to give you, since this is the first one coming up, I want to give you repeated reminders about the first exam, which starts a week from today. And what I want to make sure today that I point out is, first of all, the exam review that I told you about last week. It's going to be this Friday, 17th at 3 p.m. in this room. All right, and again, if you're not able to make it during that time, it will be recorded and posted on YouTube, so you can check it out later on. And then also, I want to make sure that I pass along some reminders about everybody's favorite building on campus, CASA, the testing center. All right, so you guys all successfully navigated CASA for the PA test. So you probably have kind of know the drill by now, but just want to make sure that we're all aware of everything you need. First of all, we're going to be doing this exam in CASA CBB, which I believe is the same one where the PA test was. That's the classroom business building. So make sure you go to the right CASA, because if you go to the wrong one, they won't let you in. And you need to make sure you bring everything with you that you need. They're only going to let you into the testing center with something to write with and a calculator, but then to make sure you're actually signed in properly, you do need your Cougar card, so the student ID card. And you have to log in with your Cougar ID and password, or CougarNet ID, I guess they call it. All right, so you can't use your PeopleSoft. There's two ways of logging in. You have to use the CougarNet one, the way they log in CASA. So you need to have both of those available. Make sure your password is not expired, that you remember what it is. So we don't want any problems with the logistics of the test, because I know it's already a stressful enough time. But with that, we're going to get on to the new material. So we're going to be starting chapter 4 today, section 1 of chapter 4. If you're one of the 1%ers who reads the syllabus, you'll know that this is going to be covered on exam 2. So this won't be on the first exam, but it will be stuff that we'll see later on, of course. So what we're going to talk about today is Vsepr, which is something you may have been introduced to if you took high school chemistry, but we're going to go through it in a lot of detail today. So Last week we talked about both ionic and covalent compounds, and for covalent compounds we primarily dealt with Lewis structures, which is sort of the arrangement of the bonding and non-bonding electrons, and we also talked about how to name the compounds. And what we're going to start with this week are some more details about the structure and bonding in these compounds, starting with their three-dimensional structures, which we can use Vsepr to predict. And as we'll get into next time, a lot of the key properties for covalent compounds do depend on the three-dimensional shape and some other things that we can predict using Vsepr. So what does this stand for? It's valence shell electron pair repulsion. And the whole idea here is we're focusing on the central atom when we do this Vsepr approach. And we're going to just try to place those valence electrons around the central atom as far apart from each other as possible. So it's really more of a geometric approach than a chemistry approach. We're just trying to put everything as far away from each other as possible. Depending on how many valence electrons are around the central atom, we're going to just arrange them so that they don't interact with each other. Because as we've talked about in other contexts, electrons repel each other, and those repulsive electron-electron interactions are destabilizing. So to minimize those, we want to make all the electrons as far away from each other as possible. So that's the idea that we're going from here. So it's a lot of spatial reasoning, a lot of basic geometry. So those things will help us as we go through and learn about these different molecular shapes. So there are two ways that we're going to categorize covalent molecules using the Vsepr approach. So one is the electron group arrangement. And so this is going to be the 3D geometric shape that both the non-ing and the non-bonding electrons occupy. So when we did Lewis structures, the central atom is usually going to have, well, it's always going to have some bonding electrons that are responsible for attaching it to the outer atoms, but then very often there's going to be non-bonding lone pair electrons. And all of those electrons are going to occupy some geometric shape, and we call that the electron group arrangement. So this accounts for all of the valence electrons. And then another important parameter for categorizing molecules is the molecular shape. So when we're talking about the molecular shape, we're ignoring the lone pair electrons in the central atom. So it's the 3D shape that only the bonded atoms occupy. So we ignore lone pairs when we're talking about molecular shape. Now the lone pairs still affect what the molecular shape is, but we don't consider them when we're classifying them this way. And the reason being that most of the techniques we have for visualizing three-dimensional shapes of molecules don't directly interrogate the lone pairs, whether they're there or not. So it's another way of thinking about this is just what the molecule looks like. So this is a more descriptive term often that tells you the shape of the molecule. Now in some cases, as we'll see, the electron group arrangement and the molecular shape can be the same thing. So if you don't have any lone pairs on the central atom, all of the valence electrons are going to be accounted for in the electron group arrangement and the molecular shape, so you would just have one descriptor for that, where the electron group arrangement and molecular shape are the same. But whenever we have lone pairs involved, we're going to have two different ways of describing the shape of the molecule, and we're going to need to be familiar with both. So some more Vsepr terms before we start running through all the different possibilities. What we'll often see, and I don't think the current textbook does it this way, but I still think it's a helpful approach, and one you may see referenced on the homework assignments, is this AXE notation. All right, so we have A, we have X with a subscript M, E with a subscript N. Those are the conventional abbreviations for this. And so A is our central atom. As I said, this all revolves around the central atom. And we're going to primarily be doing three-dimensional structures for fairly simple molecules that just have one central atom and some combination of atoms and lone pairs around it. This part of the nomenclature X is going to be any atom that's bonded to the central atom. And then E is going to be a lone pair on the central atom. All right, so when we're counting X's and E's, we only care about what's actually directly on the central atom. And then the M and N subscripts tell you how many of each you have. So by categorizing everything into this AXE form, we can really limit the number of possibilities we have. Because as you know, with covalent molecules, we have probably at least 20 different non-metal elements. We can combine them in a lot of different ways. So we could dream up hundreds and thousands of different molecules, but they're going to be all fall into a very limited set of shapes, which are going to be defined by the AXE nomenclature. And when we do these classifications, and relating back to what I talked about on the last slide, these X's and E's that we have, these outer atoms and lone pairs, are what are referred to as the electron groups. So again, when we're arranging these electron groups around the central atom, the idea is to put them as far away from each other as possible. And so the AXE notation is also going to then be specific for each electron group arrangement and for each molecular shape. So some other parameters, again, some that you probably won't see in your book but are still important to talk about. One is steric number. This seems to be a term that's fallen out of favor in more recent general chemistry, but back in the day when I learned this is how we described it. So steric number is the sum of M plus N. So it's the total number of electron groups around the central atom. And as we'll see, the importance of steric number is that it defines the electron group arrangement. So any AXE classification that gives you the same steric number, any combination of M and N that add up to be the same number, are going to result in the same electron group arrangement, regardless of how many of those are X's and how many of those are E's. So that's the importance of steric number. Now, one important note here as we're doing this and doing these classifications is that we talked about when we did Lewis structures that the bonds between the central atom and the outer atom could be single bonds, double bonds, or triple bonds, and we learned how to decide using formal charges whether we should have those multiple bonds or not. But the bond order between A and X doesn't matter for the Vsepr approach. So in some sense, even though this Vsepr approach requires a pretty good Lewis structure to get started, you don't have to have a perfect Lewis structure with all the bond orders correct necessarily, because the bond order between A and X does not really influence the geometry. It doesn't influence AXE classification. So no matter whether X is singly bonded, doubly bonded, or triply bonded, it counts as one electron group, always, for each X. Doesn't matter the bond order. So one of the examples we did was the nitrate anion, NO3-, and we saw in that one the best Lewis structure had one nitrogen-oxygen double bond and two nitrogen-oxygen single bonds, but each of those three oxygens would still just count as one electron group. So there would be a total of 3 electron groups around nitrogen. It doesn't matter that some of them have different bond orders than others. Okay, so then finally the last parameter that we're going to talk a lot about today is bond angle. So this is the angle between two bonded atoms with the central atom as the vertex. So again, from basic geometry, if you have 3 points, you can define an angle involving those 3 points. And this is a bond angle is going to be where those 3 points are 3 different atoms in the molecule. So for example, if we had a very simple molecule like H2O, we could define a bond angle between in this molecule as being this angle here, where this is the center point of the angle, and you're defining that angle, and we abbreviate that as angle sign with HOH. So the 3 atoms that are in that angle are the ones that we're going to define. So as we'll see as we go forward, the steric number, which then gives us the electron group arrangement, is also going to have some relationship to the bond orders, or sorry, the bond angles we observe, and those bond angles are going to be something we're going to need to be familiar with. All right, so let's just go through now and talk about all the different possibilities for electron group arrangements and molecular shapes. So there's this 3D interactive simulation that you can go to, which I have the website here. I encourage you to check it out because a lot of these things that we're going to do require you to visualize things in 3 dimensions, and you guys know that my artistic abilities are already limited enough in 2 dimensions, let alone 3, so we're not going to, I'm going to draw these things out, but it's better sometimes to look at the actual models. And I do have a set of molecular models in my office as well, and I'm pretty good at sharing my toys, so if you ever come visit me there, I can also show you some 3-dimensional models that you can actually rotate around yourself and sort of see how those work as well. So we're going to start from the simplest and work our way up to more complex. All right, so we have the first one, the smallest number of electron groups we're going to consider is 2. If you have only 2 atoms, AX, then it's trivially going to be linear because there's no other way to arrange 2 atoms than with a linear geometry between them. So that's obviously not what we need to talk about. But let's say you have AX2, and again the idea is to put things as far away from each other as possible. So if we go to this simulation, we can see when we have 2 atoms, 2 X atoms, and we get what's called a linear geometry. And the electron geometry is also linear. So that just puts the things 180 degrees apart, which will put them as far away from each other as possible. Okay, so that's the linear geometry, a fairly simple one. We only have 2 things on the central atom. So the name of the electron group arrangement for 2 electron groups is going to be linear. And then when you have no lone pairs, the name of the molecular shape is also linear. And the bond angle here is pretty obvious also. 180 degrees. Okay, so that's linear geometry. Now there are some molecules that have an AXE notation, which means they're going to have a central atom, 1 atom bonded to the central atom, and 1 lone pair. And this one's also pretty trivial because you only have 2 atoms. So if we replace one of these with a lone pair, now we only have 2 atoms to worry about. So the lone pair, because we have 2 total electron groups, is still going to go 180 degrees away from the bond. We still arrange things in a linear fashion, but then when we're defining the molecular shape, there's only the 2 atoms to worry about, so of course it's also going to be linear. So if you have an AXE, you're going to have your central atom, and because there's 2 electron groups, you're still going to have a linear arrangement of the valence electrons. One of those is going to be a bonding pair to X, one of those is going to be a lone pair, which we don't typically draw the line between the central atom and the lone pair, but that's one way to do it. And this is also trivially going to be linear because there's only 2 atoms. And there's no bond angle here because there's only 2 atoms. Bond angle, you need 3 atoms to define a bond angle. Okay, so that one's pretty trivial, and we should recognize then, and I don't think this will even come up because it's so simple, but all diatomic molecules are going to be linear. There's no other way to do it. So diatomic meaning 2 atoms and 2 atoms only. And these will all be linear. Alright, so if we give you anything with 2 atoms, you don't even have to think about it. But of course, as we add more and more electron groups to the central atom, things become more complicated. So now we have to start thinking in 2 dimensions when we have 3 electron groups. Alright, so if we look at the case with 3 electron groups, we're going to start with AX3, which is going to be the central atom with 3 atoms on it. So in this case, the way that we can put everything as far away from each other as possible is to make a perfect equilateral triangle where all 3 are the same distance apart in terms of the angle. And if we look at the side view of this is perfectly flat. This is a planar geometry, so there's no 3-dimensional shape to this one just yet. It's still a flat geometry. So whenever we have 3 electron groups, the electron group arrangement is going to be what's called trigonoplanar. And then if all 3 of those are x's, if there's no lone pairs involved, then the molecular geometry is also trigonoplanar. So it's just a flat triangle with the 3 x's arranged equidistant apart. And because this is flat, it's pretty easy to deduce what the bond angle is. So if we start at this x, we go all the way around, you go 360 degrees to come back to here. So we have 3 equal bond angles, so they're all going to be 120 degrees. We take that 360 and divide it up equally. So all bond angles in trigonoplanar are exactly equal to 120 degrees. Okay? And then if we have AX2E, whenever we have, again, the same steric number, so in this case there's still 3 total electron groups, but we have now 2 atoms and 1 lone pair, the electron group arrangement is the same. So we're going to start with our trigonoplanar arrangement and just replace one of those atoms with a lone pair. So when we do that, we get a geometry that looks like this, where again, the 3 electron groups are still in a trigonal plane, but now one of them is occupied by a lone pair. So if we want to classify the molecular shape, now we have to worry about these 3 atoms here. And anytime we have 3 atoms, there's only 2 possibilities for the molecular shape. It's either linear or bent. And this one is pretty clearly bent. Okay? So the lone pairs are going to determine whether there's a linear or bent geometry. So when we have 3 electron groups, we get a trigonoplanar arrangement. One of those is going to be a lone pair. The other 2 are going to be your x's. And so now we call this a bent geometry. I think your book uses V-shaped, so you might want to be familiar with that one as well. But they basically just tell you that it's that angular geometry. Now the bond angles in this case are still pretty close to 120 because it's still based, there's only one bond angle here, this XAX angle. It's still based on the trigonoplanar arrangement, so it's going to be very near that 120 degree value. But as we'll talk about more detail at the end, the bond angles are going to be a little bit less than 120 degrees in this case. So whenever you have a lone pair, that's going to compress the bond angles a little bit. You get this lone pair is going to push down on these bonds because of electron-electron repulsions, and it's going to squeeze those together a little bit, and you're going to get a slightly smaller bond angle. So it's still going to be close to 120, but not exactly. And the exact value will depend then on what the identity of A and X are. So for different AX2E molecules, you're going to get slightly different bond angles, but they're all going to be at least a little bit smaller than 120. All right, so those are the only 2 possibilities with 3 electron groups. Now let's go to 4 electron groups. And here's where you have to start thinking in 3 dimensions. So if we put 4 electron groups on, we get what's called a tetrahedral electron group arrangement. So tetrahedron is a little bit hard to visualize, but you can almost think of it as 2 perpendicular planes. So you have a plane with these 3 atoms, and then you have another plane with these 3 that's perpendicular to it. I'll come out in front for a second and show you another way to visualize tetrahedral geometry. So imagine that my body is the central atom, and my 2 legs are 2 of the outer atoms, and my 2 arms are the other 2. So tetrahedral will look something like this. So that's tetrahedral. That's another way to think about it. So again, rotating this around can help you see that a little bit better. Different views of how we can draw that. And again, the molecular models that I have are also very helpful if you're able to come by and look at those, or if you have some of your own. All right, so the 4 electron groups, we call that tetrahedral. And the reason it has that name is that if we draw an enclosed geometric shape around all 4 of those, you get a 4-sided polygon. Or is that even the right word? I don't know. But yeah, 4-sided polygon. So that's why I call it tetrahedral. Also, it does correspond to the number of electron groups, which is 4. So the way we can draw that, the common way you'll see this, and this is going to be something you'll see all the time, especially if you take organic chemistry later on, you draw 2 of them that are in the plane, and then you have 2 that are in a plane perpendicular to you. So if you draw this sort of wedge like that, that means that this bond is not flat; it's actually coming out of the board towards you. And then if we have a dashed line like this, a dashed wedge, that means we have this bond going into the board. So you can kind of sort of demonstrate 3-dimensional shapes that way, although it's obviously harder to visualize on paper than it is in real life. So that's the AX4 tetrahedral. Also is going to be the molecular shape when we have no lone pairs. And the bond angle from this one is not easy to deduce unless you're good at 3-dimensional geometry, which I'm not. And it's going to be 109.5 degrees. So that's the magic value for tetrahedral bond angles. All right, so that's the case when we have AX4. Now if we have AX3E, same number of electron groups, but we're going to replace one of these X's with a lone pair. Now when you start thinking about some of these geometries and you want to put lone pairs on, one thing we'll talk about more at the end is that lone pairs repel more strongly than bonding pairs, which is why they can often affect the bond angles. So you want to put the lone pairs as far away from the X's as possible. In most cases, it doesn't matter where you put the first lone pair. So all of these positions are 109.5 degrees apart from each other, so you can pick any of these positions and put the lone pair there. They're all exactly equivalent. Now the way to see the geometry the best is if we replace one of these with a lone pair, what we get is sort of this shape here, where it's a trigonal plane. So it's kind of like a 3-legged stool in some sense. Trigonal pyramidal, sorry. And so you have sort of this geometry here where the lone pair occupies one position, and then you have the 3 others out of the plane in a trigonal arrangement. Okay? So the way we can draw that is just starting with this same tetrahedral drawing here. We put a lone pair up top, and then the other 3 are out of the plane. And you get this molecular shape here, which we call trigonal pyramidal. And obviously, as I've mentioned multiple times, we can't ask you to draw things in Blackboard, but you do need to be able to identify the names of all of these or look at pictures of them and tell us what we have and so on. And so the bond angles for this one, they're going to be close to 109.5 because they're based on the tetrahedral arrangement, but again, the lone pair is going to compress them a little bit, so in reality, they're going to be smaller than 109.5. And it's not usually a huge difference. So as an example, ammonia, NH3, has the AX3E arrangement, and the bond angles in ammonia are around 107 degrees. So they're only a little bit smaller than you would expect because of the lone pair. All right, so we have slightly smaller than 109.5 bond angles. And then another shape you'll sometimes see with 4 electron groups is AX2E2. So in this case, we have still 4 electron groups, so they're going to be tetrahedral. But let's see then what it looks like in 3 dimensions. So we take off one bonding pair, put another lone pair on, and now we have 2 lone pairs. So this is the first geometry we see with 2 lone pairs. And again, the idea is we want to put the lone pairs as far away from each other as possible, but for the tetrahedral arrangement, it doesn't matter. All of the positions are equivalent, 109.5 degrees apart, so whichever 2 we choose for the position of the lone pair is going to give us the same one, which of course we can rotate around into different views, but it's the same geometry either way. And this, again, because it only has 3 atoms in it, the only 2 possibilities are linear and bent. And if you look at this one, it's pretty clearly a bent geometry. So whenever you only have 3 total atoms, those are your only ones. So we put the 2 lone pairs in any position that we like, leaving the X's here. If you want to draw maybe a more convenient representation of this, you can put the lone pairs sort of into and out of the plane that way. So we just sort of rotate this around to give it more obvious bent shape, but either of these are fine, and just recognize that that's the name of it, is bent. Or again, you might see V-shaped in your book. Now the difference between this bent geometry and the other one that I showed you earlier is just the bond angle. So we saw another bent geometry, which was AX2E. When you have a second lone pair here, the bond angles are going to be smaller, and again, they're going to be close to that or slightly smaller than that 109.5. All right, so you should recognize that there are 2 geometries that we classify as bent, AXE and AX2E, AX2E2 are both bent, but the bond angles for those are different, and that's a subtlety you'll need to be aware of. All right, so then moving on to 5 electron groups. We'll just go through these, and then we'll start seeing some examples towards the end. We have AX5, AX4E. So 5 electron groups is the one that's a little bit strange in some regards, because in this case we have now 2 different bond angles to worry about. So let's see first what it looks like before we define the bond angles. So if we put 5 total electron groups on, we get this geometry here, and we'll try to put it. The simulator is a little bit irritating because it likes to fold out the molecules if you try to rotate them, but here we go. Alright, so this is probably the best. I'll do it a little bit different so it matches my drawing better. This is probably the best view for this one here. And so essentially what you have here is these 3 atoms are all in a triangle, exactly like we saw for the trigonal planar case, and then you have flagpoles sticking up and above and below, which we call the apical atoms. So you have one that's perpendicular to that triangle plane going up, and another one that's perpendicular to the triangular plane going down. Okay, so that's a slightly different geometry because now we actually have 2 different bond angles, as I'll describe here in a second. All right, so for 5 electron groups, we call this the trigonal bipyramidal arrangement. And again, it's because you have a triangular plane with an apex above and below, so trigonal bipyramidal. And the way we can draw this in 2 dimensions, again using those hashes and wedges, we have a triangular plane with 3 of our x's around it, and then we have 1 above and below. And so this is one way to draw it. Another way that's perhaps even more clear is to actually just go ahead and draw the triangle. So we have our A at the center of a triangle, x's on the outside, and then we have 1 x that's perpendicular going above, 1 x that's perpendicular going below. Alright, so these are both equivalent ways of drawing the same geometry. And again, when we have no lone pairs, the name of the molecular geometry is the same as the name of the electron group arrangement, trigonal bipyramidal. And as I made reference to, there now are going to be 2 different bond angles. So the bond angle between these apical atoms in the plane is going to be 90 degrees. So as I said, these x's that stick up and stick down are going to be perpendicular to that plane, so there's going to be a 90-degree angle between this x and this x, this x and this x, and this x and that x. So there's 3 90-degree bond angles, or I guess more than 3. So you can define also the same for the bottom. So there's 90-degree bond angles all the way around. So that's one of them. And then we also have a second bond angle, which is between the atoms that are in the triangle. And as we talked about for the trigonal planar case, when you have an equilateral triangle, the bond angles are going to be 120 degrees. So you have another set of 120-degree bond angles that are on the triangular part of the molecule. Okay? So that's all well and good. We have this trigonal bipyramidal geometry, but then the complication arises when you have lone pairs now. Because as I said, we're going to start with the same basic geometry. So for AX4E, we're going to replace one of these x's with a lone pair, but the question becomes, where does it go? Because we want the lone pair to be as far away from everything as possible, and now we no longer have all of our positions equivalent. We have some positions that have 90-degree bond angles, we have some positions that have 120 degrees, so the question is, where is it better to put the lone pair? Up on this position here or somewhere on the triangle? And as it turns out, all the positions that minimize the repulsions, it might not be obvious geometrically, but it is true. The position that we always want to put the lone pairs on is on the triangular part of the molecule. So we'll see that when we do this here. If we take one of these off and put in a lone pair, I got to get it back into the same orientation now. You have that lone pair going onto the trigonal planar part of the molecule. So now you have, this is your triangle, and this is the one above and below. So we don't take anything off of these apical positions. We always put all the lone pairs out here on the equatorial part. All right, so that's the geometry. That's one way to draw it. But drawing it in this sort of standard configuration doesn't really give us the best description of its name. So let me draw it real quick. Talent needs to take a break. All right, here we go. All right, so again, we put everything like we did before. The lone pair has to go onto the equatorial part on the triangle, and then we get the x's there. Now the name of this geometry is better described if we turn this over on its side. So if we see if I can do this, we get it rotated just right, and then we have what's called a seesaw geometry. So I don't know if you guys can see that. It's really hard to do on the screen. I'm not very coordinated, but I can get seesaw geometry. So the one going up and down, and then it goes up. There we go. Alright, so the name of this is called seesaw, which is more obvious if you put it on its side and draw it like this. Alright, so this is one that for whatever reason is a difficult one for many students, AX4E, which we call seesaw. So you put one lone pair on the triangle, you get a seesaw geometry. And again, we have two different bond angles here. And because of the lone pair, they're going to be slightly different than before. This one's going to be less than 90 degrees by a little bit because of a repulsion from the lone pair. And then we still have these on the triangle that are going to be a little bit less than 120 degrees. Okay, so two bond angles, again, close to 90 and 120, but slightly different because of the lone pair. All right, and there's two other geometries that involve 5 electron groups. AX3E2, so we can have 3 X's and 2 lone pairs, or we can have AX2E3. And the idea here is, as I said, the first lone pair goes on the triangle, and all following lone pairs will want to go there as well. So if we have the AX3E2, as we can see when we remove one lone pair, sorry, we want to keep the lone pair. This, we get what's called a T-shaped geometry. All right, so that's perhaps the best way to see the shape. We can rotate it around into maybe the more conventional orientation that I had, and you call it T-shape. So now all 3 of these are all in the same plane, and you have the lone pairs again on 2 positions on the triangle now. So when we draw this out, we get our trigonal bipyramidal electron group arrangement, 2 spots occupied by lone pairs, any 2 spots in the triangle, and then we get X's there, there, and there, which gives us a T-shaped. All right, and so in this case, we only have now one bond angle to worry about. It's going to be this angle here, or the one on the that goes down as well, and they're going to be close to 90 degrees, but a little bit less because of the lone pair. So we no longer have the 120 degree bond angles because we replaced both of these other positions on the triangle with lone pairs, and we don't measure bond angles that involve lone pairs, only that involve the atoms. Okay, so we get a T-shaped geometry with slightly less than 90 degrees, and then the first 2 lone pairs go on the triangle, and so does the third one. So if we're going to add a third lone pair and go to AX2E3, that also goes out here. We only have 3 total atoms, so it has to be either linear or bent. And by putting all of the lone pairs onto the trigonal plane, we're left with the atoms completely opposite each other in a linear arrangement. All right, and there are some, this isn't the most common electron group arrangement, but there are some molecules that have this, where you're going to have, again, 3 lone pairs all distributed around the trigonal plane, and then atoms going above and below in a linear arrangement. So when we have AX2E3, because there are 5 electron groups, we start with the same electron group arrangement. We place the lone pairs as far apart from each other as possible, which is at this equatorial positions, and then the X's go up there and down there, and that gives us a linear geometry. And because we're back to linear, the bond angles are exactly 180 degrees. Okay? And the reason they're not less than 180 is because we have repulsion from the lone pairs, but the lone pair is going to push up on this AX bond, and it's going to push down equally on this AX bond, so there is no net distortion of those linear bond angles. It's going to be exactly 180 degrees for this linear case as well. All right, so we saw that there's 2 linear geometries, AX2, AX2E3, and then there's 2 bent geometries, AX2E, AX2E2, whenever you have only 3 atoms in your structure. And it really depends on the number of lone pairs that you have as well. Okay, so the last category of electron groups, the last electron group arrangement we're going to talk about involves 6 electron groups. And so what we call this is octahedral. Now the name is maybe a little bit confusing because there's only 6 electron groups, but we call it octahedral. The octahedral part refers to, again, if we draw a geometric shape around this, there are now 8 sides to that. So if we see what that looks like in a molecular model, take off a bunch of our lone pairs. We have to add 4 more of these. This is as high as the simulator lets you go, and it's as high as we're going to go. There aren't really any notable molecules that have more than 6 electron groups anyway. And so you get sort of this geometry here, and what you have, an easy way to think about this is you have 4 of your atoms in a square, and then just like we saw in trigonal bipyramidal case, you have one that points out of the square, one that points down below the square. And so we call that octahedral. And so there's 2 ways to draw this. You're going to have 2 coming towards you, 2 going away from you, so you have this square plane that's going to be perpendicular to the board as I've drawn it, and then you have an X above and below. Perhaps a simpler way to view this is to draw the square. A in the middle, X is on the square, and then again you have the 2 apical positions, one above, one below. Alright? And the reason we call it octahedral is that if you were to draw triangular faces involving each set of adjacent 3 X atoms on the outside, you would get 8 faces, 4 on the top, 4 on the bottom. So that's why the name octahedral comes about. But we'll just not worry about that too much and just focus on some of the properties of this. So the molecular geometry, the shape is also octahedral when there's no lone pairs. And the bond angles are all exactly 90 degrees. So there's a lot of bond angles in this molecule because there are 7 total atoms involved, but they're all going to be 90-degree angles. The ones on the square are obvious, and then again you have 90-degree angles between the apical positions and all of the equatorial positions as well. So because the bond angles are all 90 degrees, if we move to the AX5E electron group AXE notation, that electron group arrangement is going to also be octahedral, and it doesn't matter where the lone pair goes because all of the positions are again equivalent. So if we see how that looks, we can replace one of these with a lone pair, and it doesn't matter where we put it, they're all equivalent, and the best orientation to view the molecule is in this one here. So we've replaced one of these bottom ones with a lone pair. We have a square base with one atom above that, so we call that square pyramidal. Okay, so it's still based on the octahedral arrangement, and now we just have the one apical atom. And so it's a square. We have another X that goes above the plane of the square, and then your lone pair pointing down in that direction, and this gives us a square pyramidal geometry. Now, one subtle point about this geometry is that because we have the lone pair down here, that's going to push up on these nearby X atoms, and it's going to distort that plane just a little bit. So these 4 X atoms are no longer perfectly in a square plane, or they're not in the same plane as the central atom anyway, and then you have slightly less than 90-degree bond angles. All right, so again, always with the lone pairs, you're going to compress your bond angles a little bit, and it's going to be slightly smaller than 90 for a square pyramidal geometry. All right, and then the last one that we have to worry about, also 6 electron groups, is AX4E2. So if we have 6 total electron groups with 2 lone pairs, we want to put the 2 lone pairs as far away from each other as possible. They're the ones that repel the most strongly. So if we start with that octahedral arrangement, the best place to put the lone pairs is exactly 180 degrees apart, above and below in this orientation. So all that's left then is just this square plane of X atoms, and we call this square planar. And this is going to be the name that we use. I had a professor in graduate school who was much older and more curmudgeon-y than I am, and he always thought it was dumb that we called it square planar, because his question is, when have you seen a square that's not a plane? But this is the historic name that people use for this, and to distinguish it from square pyramidal, the one that we just showed you. So square planar is what you'll likely see. Some people just call it square to try to prove a point. The other way to draw this that's maybe more clear is just to draw them all in the same plane like this. And then you would have in this orientation, the lone pair, one of them would be coming straight out towards you, one of them would be going into the board. So that's just a rotated view of this, slightly different way to draw it. And in this case, the bond angles are exactly 90 degrees. Because again, we have equal lone pair repulsion above and below the plane, so those repulsions are going to cancel out, and you're still going to have a perfectly planar system with exactly 90 degree bond angles. Okay, so that takes us through. I guess I should show you that one in 3 dimensions just to finish out this. And so there you go. There's your square planar with lone pairs above and below the square plane, or if I rotate it towards you, we would have all of the atoms in the same square plane with the lone pairs coming out towards you and into the board. All right, so I encourage you to play around with this simulator, and then we just have a few more things to talk about before we close up today. So I've been referring to, as I've gone through this, the idea that lone pairs can cause bond angle compression. And there's also some other groups that we have to worry about that can compress bond angles. So the lone pairs are the most important ones to think about. And as I mentioned, every time you have a lone pair, it's going to compress the angles that are opposite that lone pair. So if we have ammonia, the one that I referred to earlier, it's going to be AX3E, which means it's going to have the trigonal pyramidal geometry. We have 4 electron groups, so on surface we would predict 109.5 degree bond angles, but whenever you have lone pairs, they're going to push down on all of these angles and sort of compress everything. So if you think of this as an umbrella, you're going to be closing your umbrella a little bit, and you're going to make the bond angles a little bit smaller. So lone pairs repel more strongly than bonding pairs, which is why they're going to influence the bond angles whenever they're present, especially when there's not equal, especially when there's only one lone pair and it's not canceled out by another repulsion the other way. Now, another thing that can compress bond angles are multiple bonds. So if you have double bonds or triple bonds in your structure, as I mentioned, for the Vsepr approach, we don't really care at the first level whether the X atoms are bonded via single, double, or triple bonds. But there is a subtle effect on the geometry when you have double and triple bonds in your structure. And those, because they have, a double bond is going to have 4 electrons in it, or 2 electron pairs. A triple bond is going to have 6 electrons or 3 electron pairs. Because you have more electrons in a double or triple bond, you're going to have stronger repulsion of that bond than you would for a normal single bond. So there's just more electrons there, so they're going to have a slightly stronger influence on the other bonds around them. So if we have this molecule here, POCl3, which if we're drawing the best Lewis structure has a PO double bond. This is going to be AX4. We have 2 different X atoms now, but we would still classify it as AX4. We would still normally expect 109.5 degree bond angles, but this double bond has, first of all, has more electron density and it's a little bit closer to the central atom, so it's going to push down on these other bonds here. And so what you get is this bond angle here, the OPCl angle, is going to be slightly larger than 109.5 because this double bond is going to push that chlorine a little bit farther away from it. And then the bond angles that involve only the chlorines are going to be slightly smaller than 109.5. All right, so again, you have this pushing, this extra push from the double bond that's going to fold down your umbrella a little bit. It's going to lead to slightly larger angles for the bonds that involve the double bond, and it's going to lead to slightly smaller angles for the ones that don't include the double bond. Okay, so that's another subtle effect. I don't 100% remember if that's going to be covered on the homework, but it is something we should also be aware of. And then finally, as we sort of talked about, when you're building these geometries, the strongest repulsion is going to be lone pair repulsion. So if you have more than one lone pair in your molecule, we saw that some of the AXE classifications had 2 or even 3 lone pairs. It's important to put those 2 lone pairs as far away from each other as possible. That's going to be the first important point when you're building the structure, and that gives you then the predicted geometries that I talked about. So if you have 2 lone pairs, that's going to mean even stronger repulsion, and that's going to influence the geometry as well. So, we have NH3, which is around 107 degrees. If we have H2O, which has 2 lone pairs, these lone pairs are going to be repelling each other strongly, so they're going to want to try to spread apart a little bit. And now you have two lone pairs that are pushing down on this bond, and this angle here is going to be around, I think, 105 degrees. So when you have still an AX2E2, you still have 4 electron groups. You would expect 109.5, but when you have a second lone pair, it gets compressed even more. Okay, so that's another consideration when we're comparing bond angles between two molecules. All right, so let's just do one example to close out today. Determine the molecular shape of PCl3. All right, so as I said, this approach requires a good Lewis structure. So if you didn't learn how to draw Lewis structures last week, then determining the molecular shape is going to be an exercise in futility. So we have to be able to do that first. So let's review that really quickly. So PCl3, we have 1 phosphorus and 3 chlorine. So we have to first count the valence electrons. If we go to our periodic table, all right, so our periodic table here, phosphorus is over here in group 5A, so it's going to have 5 valence electrons, 3s2, 3p3, and then chlorine is 2 over from that in group 7A, so it's going to have 7 valence electrons. Remember, we have to count valence electrons first. So we have 1 phosphorus with 5 valence electrons. Remember, Lewis structures will be on the first exam, although Vsepr will not. So we do need to know this for the first exam anyway. So we have 5 electrons from phosphorus. We have 3 chlorines, each with 7 valence electrons, another 21. So we have 26 total valence electrons. So we need to draw a Lewis structure first to be able to know for our central atom how many bonding pairs and how many lone pairs does it have, which is going to allow us to classify the electron group arrangement and the geometry. So we start again with single bonds to all the outer atoms. We complete their octets first. The outer atoms should always have exactly 8 electrons. I can't think of very many, if any, exceptions to this, unless it's hydrogen, of course. And so by doing this, we've now used 24 out of our 26 electrons. 3 octets is 24 electrons. So we still have 2 left. Those 2 go on the central atom. Now, as we talked about last time, if we wanted to know something about double and triple bonds and formal charges and all that stuff, we'd still have some more steps to go. But really, for Vsepr, you could stop here. As long as you know how many outer atoms there are and how many lone pairs there are in the central atom, the double bonds, triple bonds, things like that, those subtle points are not going to affect your prediction for Vsepr. So we don't need to worry about this. This one doesn't have any double bonds, as it turns out, but even if it did, we could just stop here. And this is going to be our central atom. We have 3 X's, 3 chlorines bonded to it, and we have 1 lone pair, which we count each lone pair as a single entity, E. So this is going to be AX3E. Each pair of electrons occupies 1 space. And so we get then 4 electron groups. That's going to be tetrahedral for the electron group arrangement. The lone pair goes in one of those positions, doesn't matter where, and that leaves a trigonal pyramidal molecular shape. All right, any questions on that one? So I encourage you to practice these. They get easier as you do more of them. I'll have a sort of a summary of this last time before we move into some new things related to Vsepr. All right, see you next time.